some time talking about large sample tests again, wall test, same thing we did before. Oh, there was a typographic error in the lecture notes, which I corrected yesterday. So if you printed it out and you're looking at it, I corrected this line. There was an inverse missing on the square brackets. We already talked about likelihood ratio. The way we do things doesn't change, and relations between the tests we're not going to change. Let's talk about decision rules for specification for a little while. How many of you have ever heard of the AIC information criteria? You look at your statistical output and you see this AIC statistic in your output. The AIC information criteria, the Bayesian information criteria, the Schwartz information criteria, R squared. These are all summary measures that are used for model selection. What was the exercise that you had to do for the first night of class? The gist of it was that you couldn't tell the difference, you couldn't distinguish between competing structural models of the world just on the basis of a little regression model. One of the other things that you could conclude from that exercise is that there's a difference between testing hypotheses and specifying the model that you like best. That is, eliminating variables or changing lag lengths on variables and things like that. So there's a difference. And in your beginning statistics class, when you had regression analysis, one of the conversations that you were supposed to have had was a conversation about the coefficient of determination. And invariably, one of the things that arises is, which model did you like better? And you were supposed to say, I like this model best because the t-statistics were all significant and it had the highest R squared. So oftentimes, people are using the coefficient of determination, the R squared, as a way for deciding which model they like better or best from a menu of possibilities. And then along came some other people who said, there are better ways to do it. AIC being one of them. The work that was done by Shannon and AIC and a bunch of other people was essentially, how do we measure the extent to which we're surprised by what we saw happen? So AIC suggested that the information content in the model that we specified, little f, can be measured by taking the log of the ratio of the true distribution of y to what I think the distribution should be. And when I take the expected value of the log of that, that tells me how surprised I am by the data that I saw, given that the truth was g. So a way to select a model is to see how surprised I am by the model that I specified, given the data. So, of course, that doesn't, so with much manipulation and a little bit of sleight of hand, AIC's suggestion was that what we could do is we could specify a model, f, and we evaluate it at the data, y, given what we believe about the world, theta. And then the more we should pay a penalty for the more variables that we throw into the model. So k is the count of the variables that we threw in. And we want the AIC, although the computer software packages do it the other way around, they have you pick the biggest AIC and switch the sign. AIC's and Shannon's suggestion was that we pick the model with the least surprise. And so we're always in the business of comparing two. We always pick the model that surprises us the least, so we can compare two of these decision rules. And so one of the things that you'll see in the finance literature especially, where they're using a lot of time series to model financial things, events, they'll say, well, we fit the following 25 different specifications of the return, the daily return, the intraday returns to IBM, with all these different lag lengths and different other intervention variables on the right-hand side. And we like this one the best because this is the one that maximizes the AIC information criteria. And implicitly, what they're doing is they're comparing the AICs amongst the different models. And they're applying them in a decision theoretic format. There's no discussion about the level of the test, right? Or a type 1 or a type 2 error. Well, suppose that And we used a normal for constructing that likelihood function. In that case, you know that the exponent in the likelihood function is the sum of squares. And so if you're comparing the AICs for two different model specifications, the nuisance parameters, the sigma squared, the 2 pi, and the covariance matrix, all that stuff drops out, and all you're left with is the sum of squares up in the exponent of the two alternative models. And what does that sound like? Sounds like you've got 2 chi-square statistic. So it turns out that if you're using the AIC to choose between two different models, implicitly you're using an F-test. If implicitly you're using an F-test and you're always picking that model which has the biggest AIC, then there must be an implied level of the test. Turns out that you can compute these implied levels of the AIC, and when you're using the AIC as your decision rule, the advantage to using that as a decision rule instead of, say, a garden variety F statistic is that it's the data that's driving the level of the test rather than your arbitrary choice. So one of the things that we see is that in large samples, when you see researchers who are stuck on F-tests, they think that's the be-all and end-all of life, is constructing an F-test. Regardless of their sample size, they always pick a level of the test to be 1% or 5% or 10%. Even when they have thousands of observations, like in these intraday stock studies, they're still testing their hypothesis at the 5% level, and they say, we reject the null. Well, if you did it right, and you use the decision rule instead of a test of hypothesis, the implied level of test by the decision rule for 1,000 observations would turn out to be really small. So you have to get a really extreme observed test statistic before you rejected the null. And that's seldom done. When your sample size gets small, the level of the test should be big, like 20%, if you have kind of a decision theoretic bent to your view of the world. So if you, like the data set on bread and meat, you did some F-tests, and I told you what level to test the hypothesis, and I just picked 5% out of the hat. But there are only 30 observations, and you're fitting a model that had 5 parameters that you were estimating. And so with 25 degrees of freedom, instead of 5% for the level of the test, it probably should have been up around 20%. So the moral of the story is that when we just plow ahead blindly applying F-tests, we make errors of different kinds. We're not conservative enough when we have big samples, and we're too conservative when we have too small a sample.